That's what we want to find. We know what the index of refraction of air is. That's 1. Okay. So what I want you to do on page 2 is to use Snell's law and use geometry to figure out, you find an equation to calculate the index of the plexiglass, index of refraction of the plexiglass based on this angle, the L length we measure, and this distance B. Okay? So, and I want you to show all your work on page 2. It's going to be using Snell's law and some trig functions. Okay? So that's, I want you to derive the equation for what the index of refraction of a plexiglass is. Okay? All right, and then on page 4, we're going to vary this angle over different ranges. We're going to measure this distance here, and you're going to calculate if we call this N1, we'll call this N2, the index of refraction of the plexiglass. Okay, that's part A. Okay, part B is similar, but instead of plexiglass, we're using water. And what we're going to use in part B is something just like this. It's a pipe, not a pie pan. It's a ceramic, what do we call this?
Pyrex.
Pyrex. Thank you. My wife is right over here. This is a glass Pyrex dish, and we're going to fill this with water. And then we're going to take a mirror and put a mirror right on the bottom. Okay? And then we're going to take the laser beam and shine it at an angle. Okay? The angles are measured using a protractor. Okay? So imagine we have a tank of water. Okay, this is our water. And this is air. And we have a glass surface here, or glass container. This is glass. And right under the glass, we put a mirror. We put a mirror right here. So then now we have a normal, and we shoot. Excuse me. We have a laser beam, an incident laser beam, and it's coming in, and here's theta 1 to the normal. And we measure theta 1. Okay. This is the index of refraction of water. We're going to get Snell's law of refraction. The ray is going to refract right here. Here's theta 2. We're going to, there's a thin sheet of glass right here at the bottom of the Pyrex, but for practical purposes, we're just going to ignore that. It's going to shift the laser beam a little bit, but we're going to ignore it. Essentially, it reflects off, so this angle here is equal to this angle here, so we get a reflection. And then, at this point, we get refraction again, and the laser beam bends back out. Okay? Where again, this would be, by symmetry, this would be theta 1, and this is theta 2. Okay? And so what we're going to do is we're going to measure this distance. We're going to fill this container up with water, and this is distance D. Okay, we're going to measure that distance. This is just the depth of water. We're going to measure that depth of water. Okay, and then we're going to measure this angle, and then we're going to measure where the laser beam comes out. So we're going to measure this distance where it comes in and where it comes out. And the way we're going to do it is something rather tricky, is in this container of water, we're going to put just a few drops of milk. Okay, so we add just a few drops of milk into the water, and we give it a good stir. Now, milk particles are well known to be scatterers of light. Okay, and so we may have to experiment a little bit. Maybe it's a teaspoon of milk, depending on how large your container is, but we add enough drops of milk very slowly to where when the beam of light goes through the water mixed with a little bit of milk, the milk scatters the light. It's kind of like smoke. If you imagine you have a laser beam, if you ever played with one of these little small laser beams, and if you have clear air, you cannot see the laser beam. But if you have smoke in the air, the smoke scatters the laser beam, and you can see exactly the ray of the laser beam through the smoke. The exact same principle here, and instead of using smoke, we're using droplets of milk dissolved into the water. Milk is a wonderful scatterer of laser light, works beautifully, and you actually can see the ray of light as it goes through the water. And so you'll be able to see exactly where it enters the water. You'll be able to see exactly where the ray of the laser beam exits the water. And so we can measure this distance where it enters the water and where it exits the water. We can measure we can measure the separation distance between these 2 points. Now, on page 5 is to use Snell's law and use trig functions, and use symmetry here. Notice that this angle here is equal to this angle here, and these theta 2's are equal. So we can use symmetry to figure out an equation for the index of refraction of water. This is index of refraction of air, and this is index of refraction of the water. So the whole thing, or what you want to do is to measure is to use algebra to figure out the formula for the index of refraction of water. Then, on page 6, we're going to vary this at various angles, and we're going to vary theta 1, and then we're going to measure the resultant change in L to see, and then use that to calculate the index of refraction of the water. Water mixed in with just a little bit of milk. Okay, question 3 is a simple question of ray tracing, where I'm asking you to trace where the ray goes. Again, you're going to be using Snell's law and some trig functions. And then question 4 on page 8 let me go back for a second here to page 7 here. Just as an example, I'm going to give you a hint on question 7 here. On page 7, question 3. The ray of light, here's the normal. The ray of light comes in, and this is theta 1. Okay? And I define theta 1 is equal to 40 degrees. So the question is, and we define, let's see, this is L1 equals 50 centimeters. This distance from here to here. Well, we know from, and this is theta 2, or index of refraction 1. This is air. The index of refraction of media 2 is water. Index of refraction of 3 is glass. back to air. So we're going from air to glass, air to water to glass, back to air. So we know that we're going to get a refraction here. Whoops, maybe I didn't draw that very well. It's going to pull inward, refract. Okay. So this is theta 2. Now we can find theta 2 again. We would use Snell's law, apply Snell's law right here. N1 sine of theta 1 equals N2 sine of theta 2. So we should be able to solve for this angle right here. But now what about this distance? One of the things we need to do is to find this distance here, because I want you to be able to, what I want you to do is find out what the total distance is to here. We'll call that x. So your job is to find out what this distance is all the way down here. You're going to get a refraction here and a second refraction here. Well, how do we do this? This distance here, we'll call this, I'm going to call this distance x1, and this distance x2, and this distance x total. Well, x1, think of it this way. The tangent of theta 2, tangent of this theta 2 is x1, the opposite over the adjacent. So it's x1 over L. Okay? So I can solve for x1. x1 is simply L, this length, times the tangent of theta 2. Okay? So this is how we do the ray tracing. We can solve for x1 for this distance here. Then we can solve for this little x1 in the same way. And then the total here is simply x1 plus x2. So the total x is simply this x plus this x. I hope that's clear. Okay? On question number 4 on page, I'm going to erase this on question 4 on page 8. This is another just working problem where you're asked to you're an electro-optics engineer, and what you have is this situation here. You have a UV laser that shoots a UV light into a fiber optic. It's a very long fiber optic, and this long fiber optic is 5,000 meters long. Okay? 5,000 meters long. And the light comes out, and then there's another fiber optic coming back to where I have a receiver. And it's what the UV pulse is a very short pulse. So the pulse travels down the fiber optic, and then right here the light travels out, and then some of the light fluoresces back, it scatters back, and there sends a fluorescent pulse, and it comes back. So the light comes back here, the UV ultraviolet light excites some chemicals here, some aromatic chemicals, and those chemicals fluoresce at a longer wavelength, and that longer wavelength, so the wavelength, this is a UV light that's coming down, but the longer wavelength light comes back up as a pulse. Okay, so basically what we have at this point, we have two pulses coming back up. We have the UV light and the longer wavelength light coming back up. This is the scattered light, and this is the fluorescent light. The fluorescent light. So it travels back up the 5,000 meter fiber. Now, what we have here is, this big graph here is what we call a dispersion. This is the index of refraction of the fiber optic at different wavelengths. Okay, so at the wavelength, at the UV light is at 300 nanometers, and at the UV light at 300 nanometers, there's a certain index of refraction of the 300. Okay. The longer wavelength light is at 550 nanometers, and here's 550 nanometers, and that has a particular. You start at 550 nanometers, go up to where it meets the curve, and then come across, and this gives you another index of refraction, but at 550 nanometers. So this is called dispersion. Okay, and dispersion basically means that the index of refraction changes with the color of the light. So this whole job is to figure out how long it takes the pulse to travel from here to here. We have two pulses. We have a 300 nanometer pulse, and we have a 550 nanometer pulse. And what I want you to do is figure out how long it will take for both these pulses to go from here back to here. So, and the assumption is that they both enter in, these two pulses enter in this fiber at the same time at t equals 0, and they'll come out and captured by the receiver at some t time later, the time later. Now these, I'll give you a hint, these two pulses travel at different speeds. They travel at different speeds because they see two different index of refractions based on the dispersion of the optical fiber. So I hope that's clear. Now on to page 9, there's a refraction drill where I want you just to, in a qualitative way, indicate where the beam of light will bend, and then there's some extra credit problems. Well, this is a very brief overview of the lab. If you have any questions, please call me or email me. Thanks.